Hey everyone, today we're presenting What the Flock, collaborative object transport using multi-agent reinforcement learning. My name is Anu, and I worked on this project with Ben Fu and Kevin Teo. Our project focuses on building and solving a simulation environment for collaborative object transport using multiple agents. Multi-agent reinforcement learning, or MARL, is inherently challenging, mainly due to the curse of dimensionality. The state and action spaces grow exponentially with more agents, and the non-stationarity of the environment. To make this tractable, we simplified the problem by focusing specifically on collaborative tasks, where all the agents are homogeneous, meaning they're identical and share the same goal. Initially, we were interested in exploring mean field game approaches, which seemed promising for handling large numbers of agents, but as you'll see later on, there were some limitations that we faced. So the specific task is to have a large number of agents cooperatively transport a bulky object to a target location. Critically, these agents operate using only their own local observations and have no explicit way to communicate or coordinate. We modeled this as a collaborative Markov game. The state includes information about the target, the object's position and velocity, and each agent's position, velocity, and relative distances. Each agent chooses an action, which is essentially a force vector, from a continuous space. Since it's a collaborative task, all agents receive a shared reward signal. Our object is to train a policy for the agents that minimizes the expected cumulative cost, which considers factors like the object's distance to the goal and potentially the energy used. The key hurdles remain the curse of dimensionality, achieving good sample efficiency during learning, and designing a reward function that effectively incentivizes the desired cooperative behavior. To study this problem, we developed the Flock environment. It's built in Python using Pygame and follows the standard OpenAI API for reinforcement learning research. The environment is a continuous 2D world containing multiple disk-shaped agents, a transportable square object, and a target location. Agents observe the target's position, their own state, the object's state, and potentially information about nearby obstacles. The reward structure combines a large sparse reward for successfully reaching the target with the denser, more frequent rewards for making progress, specifically reducing the distance between the object, the target, and encouraging agents to engage with the object.
Continuing with the approaches, as mentioned previously in the earlier part of this video, our first attempt was with mean field reinforcement learning theory, where we basically try to approximate the distribution of agents as they become increasingly large or approach infinity. We first implemented mean field Q-learning and then mean field actor-critic with shared networks over the empirical action distribution of the agents. In this case, they requires very strong homogeneity, which isn't possible, and so we tried to implement mean field control with graphons, which allow for some non-uniform interactions. But due to the novelty and limited time that we had, we only saw unstable training. I think that one fundamental flaw with this approach was that the object interactions with the agents are very locally governed, so if there were agents near the actual object and pushing it, they would no longer be in the actual distribution. And so our fallback was MADDPG and MATD3, which are both deep deterministic policy gradient methods. These differ from the traditional DDPG and TD3 methods, since the actors now only have access to local observations, and the original DDPG implementation can't handle varying objectives because you only have a single agent, or you have to have them all collaborate. And so traditional MNDDPG uses centralized training for decentralized execution, where you have a single actor-critic pair per agent. Then each actor performs the actions for agent I, or the policy network, and then the critic gives feedback on the action taken by the actor based on its actions and approximations of the actions of other agents and the remaining global observations. In our case, due to homogeneity and collaboration, we can use a single actor-critic pair, which improves sample efficiency and just the general size of the problem. In our experiments, we learned a stable policy for 3 to 8 agents in a constrained environment with few obstacles and a small window size due to our limited time. Just to give a little bit of detail into the architecture, We used an MLP for the actor and critic networks, both with 3 hidden layers. The actor had a 17-dimensional mixed observation vector, and we used ReLUs for activations between the hidden layers, and then we constrained the output using a tanh activation. This was used by every single agent and shared, so there was very high sample efficiency, and this worked due to homogeneity. Our critic network had a much higher dimension because it had to see the global action observations, and so there were actually 13 n plus 6 dimensions, and it would just output a single score. Some additional considerations were that we used exploration time steps where the fully random actions were taken. Then it just gave some different experiences to the replay buffer, and we delayed policy updates to every 2 critic updates.
So here are our results. We evaluated our implementation of homogeneous MATD3 through 2 sets of experiments. One, we compared it against the stable baseline's TD3 implementation, and 2, we varied the number of agents. For all experiments, we attempted to use the same parameters for TD3 and MATD3. These were optimized by hand, so the performance below is not strictly optimal. And because of our limited time, we used a 300 by 300 size window for our environment with no obstacles. So as you can see in this graph, TD3 fails to converge towards solving the environment, even with 25,000 exploration steps for both 2 and 4 agents. It does, however, improve slightly in the 2 agent case, peaking at about 200 reward. MATD3, on the other hand, generally performs better in both situations. It does not converge in the 2 agent case, but begins to reach solution consistently, slightly before the 90th episode of training. And looking at these few graphs, we can see that MATD3 performs reasonably well for 8 agents and 4 agents. For 2 agents, it does not really converge, and for 16 agents, it also struggles at conversion. So basically, we're doing really well with 8 and 4 agents. We're getting what we want to see, but for more agents, we're going to have to do some more work. As for limitations in future directions, we're hoping to address mean field instability, sparse reward sensitivity, hyperparameter fragility, and overfitting to our sandbox. So yeah, these are our references if you want to check them out. And thank you for listening to this presentation. We wish you well, and we hope at one point during this presentation you said, what the flock? Thank you.